Okay, so recording has been started. Yesterday we just kind of talked about the assumptions that are needed for a linear regression model. Today we're going to look at inferences about the slope of that model. So again, we're in our notes packet from yesterday, page 6. So just like how yesterday we said that the true population regression line is unknown, so we estimate it, that kind of goes for beta as well. Beta, which is the true value of the slope of the population regression line, is unknown, so we use B, which is the slope of our least squares line, to estimate it. When the 4 basic assumptions that we talked about yesterday are satisfied, then the following 3 statements would also be true. The first one being the mean value of B is beta. Oh, come back. There we go. So the mean value of B is beta. The standard deviation of the test, or sorry, not the test, of the statistic B is sigma divided by the square root of S sub xx. Now, let's think about something for a second. B is a statistic, but yet our formula has a parameter in it. So B is a statistic, which means we're estimating it for beta, yet our formula for the standard deviation of B has a parameter for beta. We'll come back to that here in a second. The statistic B has a normal distribution, and this is a consequence of the model assumption that the random deviation E is normally distributed.
I'm Phil. I go to your book, sorry.
So since sigma is usually unknown, because beta is usually unknown, instead of using sigma, we're going to use SE for the standard deviation of our model. SE we calculated yesterday. And again, we use SB for the standard deviation of the statistic. So now everything's a statistic. We're not dealing with parameters based on an estimate. Everything is a statistic. Okay, so let's look at a confidence interval for beta. As long as our 4 basic assumptions are satisfied, we can make a confidence interval for beta. which is, of course, the slope of our population regression line. To do that, we'll use B. So it's B plus or minus, just like we've done in the past. We don't have to write out T critical value. Just say T crit times S sub B. And this is the same S sub B that we just wrote the formula for. So SE over square root of S. And we calculated this value yesterday. Calculated that value yesterday. And the T critical value is based on n minus 2 degrees of freedom. You have to remember, we're having to estimate alpha and beta when we do a regression. So we lose 2 degrees of freedom here. Okay. And then if we took it a step further and we did a multiple regression, which I wouldn't have to worry about for this class, but I mean, you could. It'd be 1 for each thing you estimate. That's right. Okay, let's look at an example. So is cardiovascular fitness, as measured by time to exhaustion from running on a treadmill, related to an athlete's performance in a 20-kilometer ski race? So to answer this question, they let X be the ones that did the study. So okay, X is going to be treadmill time to exhaustion in minutes. So how long can you run on the treadmill until you're exhausted? Some more humorous note, I'm wondering what they call exhaustion. Do they like crank the speed all the way up and have you run until you just fall over from being tired, or do they just say, okay, I'm done, that's all I can do, and step off? Anyways, that's your X. Y is the 20-kilometer ski time in minutes. And this study was actually done and published under the article Physiological Characteristics and Performance of Top U.S. Biathletes. And I'm guessing that's the next one is the name of the publication it was in. Medicine and Science and Sports and Exercise. So there's our data. First thing we want to do, make a scatter plot. In case you haven't caught on this semester, it tends to be the first step for analyzing data. Visualize it. So I gave y'all a set of axes. I want y'all to take a second and plot the points.
Maybe in here, the one you just asked them.
Okay, so on your scatter plot, it should look like that. So if we look at the plot, what do y'all notice about it? What are some observations you can make from the scatter plot? Negative. Yeah. Medium to strong correlation, negative correlation. Does it appear to be linear, quadratic? What do y'all think? Linear. Yeah. So the plot shows a linear pattern, and the vertical spread of the points does not appear to change over the range of x values. So if we assume the distribution of errors is approximately normal, then we could say a linear model is appropriate. Okay, so what we want to do now is look at our slope. We're going to see if we can make a confidence interval for the slope. Before we do that, though, let's look at the regression output down below. So we're going to skip this little part of the problem and go to the output. So what do y'all think this first one is up here? This first piece of the output. Ski time equals 88.8 minus 2.33 treadmill time. What's this represent? This piece is our equation of the regression line. So on the output, the first thing they give you is the equation. Now, Minitab gives it to you. Not all software will say, hey, here's the equation. If you're using a software like R or SAS, that's another popular program. It's called SAS, S-A-S. They don't, from my experience at least, they don't tend to tell you the regression line. Their output will start here. So this first piece is the regression line. Then the constant is going to be your y-intercept A. The next one's your slope. So the predictor, they use the variable treadmill. That's your slope. The 0.5911, that's the standard deviation of B. That's the new one that we just talked about on page 6. It's SB. The S equals 2.188. That's your standard deviation of your errors. That we talked about yesterday, and we've also talked about in chapter 5. What's this 63.4%? What's that represent? That's 100 times your R squared value. So that kind of gives you a hint. RS cubed, R squared. Now this R squared adjusted, we don't use that in simple linear regression. What that's used for is that actually, just so you kind of know about it, it penalizes you every time you add a new degree to the equation. So let's say you look at the data and you're like, I think this is more quadratic than Will and Justine. Yeah, this is UIL stuff for Saturday. So what the adjusted R squared does is it penalizes you for trying to get the model to fit better. Because like we talked about, the higher the R squared, the better the model predicts. Well, realistically, you could have, let's say you have, I don't know, let's say you have 10 data points. It's like, okay, fine. I'm going to make x to the 10th. I'm going to have 10 predictors just so I can get a perfect fit. Well, your adjusted R squared will drop drastically because then your model is really inaccurate. That's what that does. We're not going to really worry about it much. I just wanted you to know what it was. Okay, sum of squared residuals. We calculated this by hand, but it's often part of the output under the analysis of variance, or you might also hear this called ANOVA. We're not going to go into the ANOVA test, but we will use some of its output. Essentially what it's doing is testing to see how good your model is. And without going into much detail, this is called the F test. The higher this number, the lower your p-value. And as we've learned from our other hypothesis test, is a low p-value good or bad? A low p-value. That's good, right? You can reject. So a low p-value here means we have a good model. So this model is at least for this, this tells us it's a decent model. Like I said, that's 43.097. That's your sum of squared residuals. The 117.727, that's the total sum of squares. And the 4.789, that's your model variance. The variance of your errors. Notice that this 4.789 is just this squared. Okay, so we've talked about the output. Oh, I forgot to mention the 9 under the degrees of freedom here. That's our n-2 degrees of freedom. So the degrees of freedom on your error is the appropriate n-2 degrees of freedom. Okay, let's go back and work through that example we skipped now. Now that we know where to get our numbers from the output. Okay, so find the 95% confidence interval for the slope. Well, let's start by writing our formula. B plus or minus T crit times SB. Okay, what did the output tell us our slope was? Yep, what was that full decimal? Negative 2.33. I'm sorry. Plus or minus. Okay, now we've got to get the critical value. So degrees of freedom would be what? 9. That's right. And then it's a 95% confidence interval. So we're going to have to divide alpha by 2 before we look in our table. Alpha is 0.05. So we're going to want to look at the 0.025 level. So there's our degrees of freedom. That's the column we want to look in. You don't have to pull your table out unless you have it readily handy. So I'm going to put one up on the screen. Okay, let's see. There we go. So we need me to zoom in so we can actually see stuff. Too far. Okay, so 9 degrees of freedom. 0.025. That means our critical value is 2.262. 2.262. And then what was the standard deviation of the slope? I mean, we could calculate it, but they actually gave it to us in the output. I'm sorry, 0.5911. Okay, so let's calculate our bounds. We need a lower bound and an upper bound. Whoever gets the lower bound, if you want to say it, let's do it to 2 decimal places. Yep, negative 3.67. And what was your upper bound? Yep, so the 2 decimal places, what would that be? So there's our interval. Now, the way you would interpret this, I mean, I'm not talking about like officially writing the sentence for it, but just let's say you're looking at some output and I say, here's your confidence interval for the slope. Where this helps you is you can see, is there a good relationship? Well, you know that if 0 is not in the interval. So is 0 in our interval? No, that means there is a substantial relationship. If 0 was in the interval, that means the slope could be 0, which wouldn't tell us much of anything. So 0 is not in there, so there is definitely something going on here as far as a relationship goes.
So, if you have an interval like negative 0.01 to negative 0.01 to positive 0 is still in it. So that is better than anything else.
Yeah. Because that means 0 is still in the realm of possibility. Yeah.
So when you just get down to like a 90% confidence interval,
I mean, if you wanted to fudge the numbers and make it in your favor, yeah, you could. Yeah. Yeah. You could. Yes, that's right. Confidence would keep going down. Now, with that being said, usually the intervals wouldn't be that drastic. The reason, like if you were analyzing an actual data set, they would usually be much closer because you have more data points. I mean, you got to remember, we only have 9 degrees of freedom here. So that's why our interval is fairly wide. If you had more, you had 20, 30, 40 data points, that interval is going to get smaller and smaller and smaller. Okay, so we're 95% confident that the true average decrease in ski time associated with a 1 minute increase in treadmill exhaustion time is between 1 minute and 3.7 minutes. Now, these are positive here because I've already said it's an average decrease. So that's why I didn't have to come in here and put negatives. I've already said we're decreasing. If we decrease a negative amount, doesn't mean we're increasing. Questions on this example? Okay, let's flip the page. So confidence intervals are one way to tell if you have a significant slope. Another way to tell is through, once I get through all this that we've already done, hypothesis testing. So our null hypothesis is that beta is equal to some hypothesized value, just like we've had our hypotheses in the past week. Our variable equals whatever value. Usually, though, this value is 0. The hypothesized value is typically 0 because we're doing a model utility test. If we fail to reject, that means we're saying, well, we can't prove it's not 0, so the slope must be 0. Pretty darn close to it. So then we have our test statistic. T equals B minus your hypothesized value divided by the standard deviation of B. Now, this looks scary, but it's not as bad as it seems. Remember, this top piece we said on the previous page, this is SE. The bottom piece is S, so that's X. So SB looks intimidating, but if we think back to what it actually is, it won't be so bad. And again, this test is also based on n minus 2 degrees of freedom. So with our hypothesized value typically being 0, if it is 0, so I'm going to say if equal to 0, this just becomes B divided by SB. If the hypothesized value is 0. If it's not, then we couldn't simplify it like that. And as with any hypothesis test, I still see some writing, but I'm going to move on to the alternative hypotheses and talk about those. As with any, our alternative hypotheses are the same. Beta can be greater than our value, less than the value, or not equal to the value. And that determines what kind of test you do and how you want to look at the p-value. So if beta is greater than the hypothesized value, that means we have a right-tailed test, just like we've had in the past. Less than means we have a left-tailed test. Not equal to, we've got a two-tailed. When it comes to slope and doing the model utility test, this is our most common. Alternative hypothesis. Because we're concerned with, is the slope 0? If it's negative, great, that says something. If it's positive, great, that says something. But if it's 0, it doesn't tell us anything. So the last one's our most common, but we can do any of them. Let's look at some assumptions for this test. Of course, your 4 basic assumptions for a linear regression model must be met, which are the distribution of errors at any x has to have a mean of 0. The errors have to have a mean of 0. The standard deviation of the errors is sigma, which does not depend on x. The distribution of the errors at any particular x must be normal. And the random deviations must be independent. So let's suppose we have a least squared line that's horizontal. And we're wanting to try to predict weight based on height. There's our line. Is this line useful in predicting weight based on height? No, it's not. What's the slope of this horizontal line? 0. A slope of 0 means there is no linear relationship between x and y. So that's why we're always concerned. Is the slope 0? Is the slope 0? Because if it is, there's no relationship, at least no linear relationship. Now, if you have this same line and then your data look like this, well, clearly, yes, there's something going on there. But as far as a linear relationship is concerned, no linear relationship. So we need to check for model adequacy. The simple linear regression model is what we mentioned earlier. Y equals alpha plus beta x plus your error term. And like I said yesterday, this is typically an epsilon. Where epsilon or E represents the random deviations of the observed Y values from the population regression. The assumptions for a simple, if you look back at your assumptions, you'll notice that they all are based on the random deviations. We're not basing them on slope. We're not basing them on the intercept. Everything is based on the deviations. So when we look at the fit of a model, that's what we're going to focus on still, the deviations. If we knew the deviations, we could examine them for any inconsistencies with assumptions. But we don't know ahead of time what they're going to be. So we're left with looking at the residuals, like we did in Chapter 5. We're going to use the residuals to check our assumptions. And to do that, you could use normal residuals or standardized residuals, where you do the residual divided by the estimated standard deviation. But it's so tedious to do by hand that usually you just look at statistical software and let it tell you the calculation results. You don't want to do these calculations by hand. If you have a large standardized residual, you probably need to turn around and go look at that observation. Was there an error in recording the data? And we're not going to go into all the different kinds of errors. When I took statistics in college, we had to know each and every one by name. And I think one of them was called like a transcribing error, meaning maybe you observed the person ran 100 feet, but you're at 10 feet. I mean, you left the zero out, but when you examine the data, the zero is going to make a big difference. So there's different kinds of errors in recording data. Was there non-standard experimental conditions? Or was there an atypical experimental unit? And then once we look at the residuals numerically, we can go back and make a normal residual plot or a standardized residual plot, which is a plot of the X and standardized residual pairs. So we did residual plots in chapter 5. Regardless of whether we do residuals or standardized residual plots, we want one that has no patterns. We don't want curves, we don't want wedges, we don't want one point to be further away from the others. We just want it to look random. So let's look at some plots. I'm not going to be able to put them up and then talk about them because as I put them up there, it tells you the answer. So look along with me on your packet as we go. Well, let's look at that first one, that first plot on your packet. What do y'all think about that one? Do y'all see any patterns? Are there any points that are further away? You see anything going on that plot? No? That's what you want it to look like. That's a good, desirable plot to have. There's no pattern. There's no point that's further away from the others. It's just a random smattering of points. Okay, what about the next one? Again, I can't put it up there because it'll tell us the answer. If you look on your packet, just the next one to the right, is there anything going on that one? What's happening with it? It's what? Yeah, it looks like something maybe quadratic in nature is going on. There's definitely a curve. This plot tells you that you probably should use some kind of model that's curved. A linear model is not cutting it. There's got to be some curvature involved. What about the next one on that row? Starts off linear and then kind of breaks off. Yeah. So we call that a wedge shape. This one is wedge shape. I mean, you can, kind of looks like they have a wedge here. So this is not a good model either. In this plot, the standard deviation of the residuals increases as the x values increase. So a straight line model might still be appropriate, but we should use a weighted least squares line. That goes into too much depth, so we're not even going to go there. There's just something's going on in the data. There's a wedge going on there. And then what about those last two? That's right. There's outliers. Those last two both have outliers. So both of these plots contain points that are far away from the others. And those outliers can have substantial effects on your regression line. So those are ones that's in each of those cases, that's where you would go find that observation and try to see, was there an error? Did the person that was entering it type 72 instead of 27? Stuff like that. Okay, so this isn't in your packet here, but we're going to look back at that biathletes example and kind of talk through it. So, like I said, this isn't in your notes. So let's talk through the biathletes example. So we found the slope. We said, yes, there's definitely some kind of relationship going on. So let's look at a normal probability plot of these standardized residuals. We looked at this in chapter 5. This is that one where you have your normal score and the residuals, and you want them to fall all along a line. Hopefully you remember doing something like that in chapter 5. Everything kind of falls along the line, so that tells us that there's no reason to doubt our model, our linear model. The random deviations still appear to be normally distributed. So then if we were analyzing this data, once we saw that, we're like, okay, fine. Let's take it a step further. Let's look at standardized residuals. So I do the standardized residuals versus my x values. Do you see any pattern in that plot? No. So far we're looking good. It doesn't show any evidence of pattern or a wedge or anything like that. So we can look at just the normal residuals and see if we see a pattern. No pattern there. And they look the same. You notice the plots both look pretty similar. Then we can even go further and do the residuals against y hat. And again, they would look the same as the ones up here on the screen there. So a linear model is acceptable for this data. Okay, we're done. So tomorrow we're going to deal with mini-tab output and really talk about interpreting it. I mean, we talked a little bit about the output today. I'm just going to take that instead of saying, oh yeah, this is what all this is. Well, let's interpret it. Our slope is this? Okay, what's that mean? This is the r squared? Great, what's that mean? That's what we're going to do tomorrow. So, okay, we are done for today.